So it is a honor and privilege to introduce such an eminent personality, Professor P.V. Aruna Chalam Garu, who is a reputed researcher and professor, academician, and whatnot. Professor Aruna Chalam Garu was born at Karveti Nagar, Chittoor, and he completed his intermediate and BA Mathematics in Sri Venkateswara College, Tirupati. And he got first class and first rank in MA degree in 1955. And he worked as a lecturer in Madras, Kanchipuram, and Tamil Nadu. Later, he joined as a research scholar in IIT Madras. And then he completed his PhD from IIT, and his specialization is in applied mathematics. Later on, he joined at SV University, and he positioned different categories like Dean, Controller of Examination, and retired as a principal at SV University Arts and Science Commerce in 1995. He also acted as visiting professor in the University of Florida, USA, and he's the first vice chancellor to Dravidian University. He is also the in charge for Sri Krishna Devaraya University and also in charge vice chancellor for Sri Padmavati Mahila University. And he got lot of many more laurels in his career, and he is nominated as member UGC Advisory Committee of DSA Mathematics program, and he elected as president of Indian Mathematical Society for the year 2001 and 2. He is one among the founding members of Gandhi Bhavan Trust, Tirupati. He got elected as council member, once an executive committee member, twice an Indian Science Congress Association from 2005 to 2008. And after his retirement also, he is acting as a consultant, advisory and committee member for many organizations. And he has taken part in different writing different books in mathematics in junior colleges as well as in the degree. He got several awards and honors. Few of them are, he was a Fulbright scholar of University of Wisconsin, USA. He got elected as fellow of the National Academy of Sciences, Allahabad. He got Best Teacher Award in 1987 by Government of AP and Telugu Academy Award in 1988 and whatnot. And the Honorable Prime Minister, Dr. Manmohan Singh, honored him by presenting Professor P.C. Mahalombi's birth century gold medal in 2008. He published more than 45 research articles in mathematics, and not only mathematics, he has written many articles in general papers, more than 100 in science, education, literature, social science, social service, and philosophy also. And he has written many prefaces and introduction to more than 65 books. And he has attended more than 25 national and international talks, and his research interests include ancient Indian mathematics. And he is guru of many eminent professors who are working in University of Hyderabad, and few of them are resource persons for our five-day FDP program. They really felt happy by looking at the flyer that their guru is on board. And he is an author in translating Robert Kennigal's book, Biography of Srinivasa Ramanujan, titled The Man Who Knew Infinity. So with this brief introduction, it's a big profile that it takes minimum half an hour to 45 minutes to read out all these things. And it's very honor and privilege from the Commissioner of College Education to have a beautiful interaction with Professor Aruna Chalam Garu. Now I request the Aruna Chalam Garu to start his presentation on Harmonic series. Thank you so much, sir.
I deem it an honor to be invited to participate in this faculty development program that is being organized under the auspices of the Department of Collegiate Education and also Department of Technical Education, Government of Andhra Pradesh. I am deeply beholden to the Commissioner of the Collegiate Education, Shri Nayak Garu IAS. The program is being organized by several friends, and I am grateful to all of them. Dr. Anil Kumar, Dr. Pende Kanti Sridhar, Madam, who introduced the program to the listeners this morning, and to another friend who has taken pains to say very nice things about me. I express my profound gratitude to all these people for their kind gesture. Now I have chosen to present before you a very elementary topic in one sense and a very advanced topic in another sense, namely the harmonic series appears to be in the air right from the times of Pythagoras, when he dabbled with the musical tones. He found the deep lying relationship between the fundamental tones and other tones and the harmonic series. The very name for this series is derived from its connection with music and musical tones. So having began its journey from the times of Pythagoras, it has been a celebrated infinite series in the literature, talked about both by beginners as well as by people who are in advanced stage of research related to Riemann hypothesis. So that is the status of this innocent looking infinite series, sigma 1 by n. That means 1 plus 1 by 2 plus 1 by 3 plus 1 by 4, etc. Slide. The harmonic series. It has been established that it is a divergent infinite series. I have already explained to you a little while ago that the name originated from the concept of overtones or harmonics in music. The wavelengths of the overtones of a vibrating string are 1 by 2, 1 by 3, 1 by 4, etc. of the string's fundamental wavelength. Every term of the series after the first is the harmonic mean of the neighboring terms. This is another interesting feature about the series. The phrase harmonic mean likewise is derived from the literature of music. Now at the degree level, both in algebra and in calculus, people talk of harmonic series, more so in the classes of algebra. While discussing the concept of convergence and divergence, harmonic series is invariably referred to as an example of a situation where the necessary and sufficient conditions of convergence are stressed upon. People say and prove that for an infinite series to converge, two conditions are two aspects of the conditions, a necessary and sufficient conditions. One of the necessary conditions is that its nth term should be tending to 0. Take, for example, the nth term of the harmonic series, which is 1 by n, and 1 by n tends to 0 as n tends to infinity. But this is not sufficient, because the very harmonic series where the nth term is tending to 0 is not convergent. It is a divergent series. So that means there are some more conditions to be satisfied to make a series to be convergent. So teaching this point, almost all teachers of mathematics will cite as an example and a counterexample this harmonic series. Now, coming to the character of the series. By character of the series, I mean the convergence and divergence properties. So we have already stated that the divergence of this series has been established long ago. First person to prove very simply using methods which anybody can appreciate was Nicole Oresme, a French mathematician of the 14th century. The proof given by Nicole was buried for a long time. People were not aware of the contribution of Nicole regarding the divergence of harmonic series. Then mathematicians started to tackle the problem in a different way. Amongst them, mention must be made of the contribution of Pietro Mingoli, 1650, Bernoulli, Jacob Bernoulli, the famous Bernoulli family, for 3 generations. More than 10 persons were mathematicians. This is a unique feature in the history of mathematics. An entire family spread over for 250 years, indulging in mathematical research, using extraordinary results in the subject. So that is the greatness of the Bernoulli family of Switzerland. The first man from that family was Jacob Bernoulli. In 1689, he gave a proof for the divergence of harmonic series. His younger brother, Johann Bernoulli, in the year 1742, gave another proof independently. Johann Bernoulli is to be remembered always because Leonhard Euler, who dominated the mathematical scene of the entire 18th century, was a student of Johann Bernoulli. So Johann Bernoulli presented to the world of mathematics a mathematician called Leonhard Euler, who needs to be counted as one of the all-time great mathematicians of the world. For a long time, Archimedes, Newton, and Gauss are being considered as all-time great mathematicians. Into this gallery, the name of Euler also is being included. People who celebrated the tricentenary of Euler in the year 2007 realized the enormous contributions made by Euler to the field of mathematics. Though, depending upon the inadequacies of mathematical equipment available during the times of Euler, he might have gone non-rigorous in some situations. So that did not bar him from being classified as one amongst the all-time great mathematicians. So that Euler was trained by Bernoulli Johann. Therefore, both brothers, Jacob and Johann, from the Bernoulli family, proved independently the divergence of harmonic series. There are 20 proofs which can be easily understood by degree level students about the divergence of harmonic series. There is an article by name, "The Harmonic Series Diverges Again and Again," by Stephen Hifowit and T.A. Stamp, AMA TYC Review, Spring 2006. About 30 more proofs are collected by Stephen in 2006, which are made available in the net, but not yet published. Perhaps he wants to add some more proofs before getting them published. We know that there are more than 300 proofs for Pythagoras theorem. A proof of Pythagoras theorem was given by one-time president of United States of America also. So, though not so much of popularity, there are so far about 50 different proofs for the divergence of harmonic series given by several mathematicians. It is of interest to note that famous Leibniz also gave a proof independently for harmonic series, for its divergence. Now let us have a look into the beautiful proof given by Nicole in the year 1350. So in a way, it is a sort of comparison test. When we teach classical algebra for the degree students, we present before them several tests to know the qualitative behavior of an infinite series. The comparison test is the first one, the ratio test, the integral test, the Rabi's test, the Kummer's test, the Dirichlet test. So like that, there are several tests. Depending on the series, we take the help of these tests and establish the qualitative behavior of the infinite series. Now you see how Nicole used this comparison test. You see the first line, we have the various terms of the infinite series of the harmonic. Then it is greater than 1 plus half. So 1 is 1, half is half. Then the third and fourth terms are 1 by 3 and 1 by 4. For 1 by 3, he puts 1 by 4, replace 1 by 3 by 1 by 4 and keep 1 by 4 as it is. Next 4 terms, 1 by 5 to 1 by 8. 1 by 8 is the least. So replace these terms by the least, 1 by 8 plus 1 by 8 plus 1 by 8 per 1 by 8. Then from 1 by 19, 1 by 9 to 1 by 16, there are 8 terms, and these 8 terms are to be replaced by 1 by 16 and 1 by 16, 1 by 16, 1 by 16. Now you see the next stage will be 1 plus half as they are. Instead of 2 1 by 4s, we add them, you get half. You have 4 1 by 8s, you get half. So this is very clear. So we have established that the harmonic series in toto is greater than another infinite series where the first term is 1 and all terms are half, 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 etc. So the series on the right hand side, which consists of 1 plus sigma 1 by half, is obviously a divergent series. Its limit tends to infinity. Therefore, by comparison test, the harmonic series is indeed a divergent series. Now, notationally, you can express this fact by sigma n is equal to 1 to 2 power k 1 by n is greater than 1 plus k by 2 for every positive integer k. Now, a word about the integral test. The integral test is the result of applying the methods of calculus. So take the curve y is equal to 1 by x. If x takes all positive integral values, you get as members of this the infinite series 1 plus half plus 1 by 3 plus 1 by 4 plus 1 by 5, etc. You know the area under the curve y is equal to 1 by x is the result of adding up the areas of the rectangles that is drawn in the figure. The first rectangle is of area 1. The second rectangle's area is half. The third rectangle area is 1 by 3. Therefore, the area under the curve y is equal to 1 by x. 1 is less than or equal to x, less than or equal to infinity, is infinite because it is obtained as a definite integral of the integrand 1 by x taken between the limits 1 to infinity with respect to x. We all know that logarithm unit of integral of function 1 by x is log x, and the limits from 1 to infinity leads us to the infinity. Therefore, this is the integral test to establish the divergence of the harmonic series. Now, some qualitative aspects we will see, or some quantitative aspects let us see. Its divergence is very sluggish. It diverges very, very slow. For example, if you examine the partial sums, the first term, of course, is 1. The first and the second terms, that is S2, sum up to 2 terms is 1.5. Take sum of the harmonic series up to 200 terms from the first term. It adds up to 6.87803 approximately, cutting to 5th decimal place. And then take 1000 terms and you get S 1000, that is equal to 8.48547. Then go to 1 lakh terms. S 1 lakh is equal to 13.0 0902. Now, if you add up the first 10 to the power 43, a horrendous huge number, 10 to the power 43 terms, if you sum all these 10 to the power 43 terms, the sum will not exceed just 100. So this shows that how slow the divergence is with reference to the harmonic series. Then let us touch upon the alternating harmonic series. So if you take positive, negative terms, 1 minus half plus 1 by 3 minus 1 by 4, etc., this converges to log 2. So this is a convergent infinite series. So alternating harmonic series is a convergent infinite series. Now it can be proved very easily. The infinite series for log 1 plus x for all x plus 1 greater than 0, which gives us the domain of the function. The function is represented by an infinite series, x minus x squared by 2 plus x cubed by 3 minus x power 4 by 4, etc. for all x, such that x is greater than minus 1. That is, x plus 1 is positive. Put x is equal to 1, you get alternating harmonic series. Now, while teaching this concept, we also bring in the idea of absolute convergence and conditional convergence. Now, this series, alternating harmonic series, is convergent, of course, but it is not absolutely convergent. By absolute convergence, we need the corresponding harmonic series with all positive terms also should converge. So sigma un is absolutely convergent if and only if sigma mod un converges. So this is the theorem which we all know. So according to that theorem, the alternating harmonic series is not absolutely convergent. We call as conditionally convergent series. Now, very interesting results are being obtained, or they were obtained by several mathematicians by playing with alternating harmonic series. So alternating harmonic series are any conditionally convergent series can be taken, and we can prove that this sum of such series is different. So we can prove in one way the sum of an alternating convergent harmonic series, alternating series, that is conditionally convergent series, is one thing, S1. By some other method, by rearranging, we can show that its sum is a different figure, S2. It can be S3. So whatever sum we want, we can devise a method and get at that result through some algebraic steps for the conditionally convergent series. So this is altogether a different topic which is not relevant for the present times. So our purpose is now to touch upon the fact that from harmonic series, by taking alternately positive and negative terms, we get the alternating harmonic series which converges to log 2. Then we have prime harmonic series. Prime harmonic series is formed by the reciprocals of all the prime numbers P1, P2, P3, etc. A very epoch-making result given to us by the great Euler, who proved that the prime harmonic series is divergent. Its importance can be seen from the fact that way back in the 3rd century BC, Euclid very ingeniously established the fact of the infinitude of primes. That means primes are unlimited. There is nothing like the largest prime number. If you say P is the largest prime number, I can produce the next prime number, P plus or P2, which is greater than P1. So that disproves the fact, or that disproves our assumption that we have marked a particular number as the largest prime number. Therefore, from 3rd century BC up to 18th century, mid-18th century, nearly 21 centuries have elapsed before a second proof was given for the infinitude of primes. So that was given by Euler. Therefore, we hail Euler. People say, read Euler, he is the master of all. So Euler proved that this series is divergent, an important result regarding the infinitude of prime numbers available in the literature. Then we have general harmonic series. The general harmonic series is sigma 1 by an plus b, a not equal to 0. If a is equal to 0, no series at all. We don't get any series. We'll just get 1 by b. That is all, 1 by b plus 1 by b plus. What is of interest there? A and b are real numbers, and b by a is not equal to 0, or it is a negative number. It is not a negative number. It is not equal to 0, b by a. So under these conditions, sigma 1 by an plus b, let us call that as the general harmonic series. By limit comparison test with the harmonic series, the general harmonic series can be proved as a divergent series. So it is just a comparison test, because we know already the simple harmonic series, just harmonic series, ordinary harmonic series is divergent. Comparing that with this one, taking the limit, D'Alembert, the ratio, limit of the ratio, we get the divergence of general harmonic series. Then the next important series is the P series, sigma 1 by n power p. This p is, say for example, p is for the present, let us say, no, it can be any real number to start with. So let us first say p is equal to 1. If p is equal to 1, you recover the harmonic series. So the P series, when P is equal to 1, diverges, obviously. When P is greater than 1, it is called over-harmonic series. This over-harmonic series converges to the sum, usually denoted by zeta P. We'll come to that a little later, why it is denoted as zeta P. So one thing is, it converges to the sum. It is a convergent series. Now you know there are two aspects about infinite series: the qualitative aspect and the quantitative aspect. The qualitative aspect is to declare whether a series is convergent, divergent, or oscillatory. So this is the character, general character of the series. This can be done easily. There are methods, tests available in the literature to help us to decide about the qualitative nature of an infinite series. If an infinite series is divergent, okay, we can't do much about that, so we set it aside. If it is an alternating series, we have seen that we can play with it and produce several types of sums. That is a game that we can play. Now, coming to this very important group of series, convergent series, and series is convergent, the next question is, to what limit the sum converges? The sum of n terms of this convergent series, let us denote it by Sn. What is the limit of Sn as n tends to infinity? That very limit we define as the sum of the series. The sum of the series is defined because it is not 20 terms or 30 terms whose sum can be added. Adding the terms, we get the sum of the collection of finite terms. So that is not the case for infinite series. The infinite series contains infinity of terms. Therefore, our concept of the sum of a few numbers fails here. So a new concept was introduced. What is that new concept? Take the sum of the n terms and compute the limit of Sn as n tends to infinity. And that is defined as the sum of that convergent infinite series. Then, after over harmonic series, we come to the case when P is less than 1. When P is less than 1, the series diverges. Can we name this as under harmonic series? Just for fun, because that is over harmonic series. Let us call this as under harmonic series. Now, summing up, this P series converges for P greater than 1 and diverges for all P less than or equal to 1. So that is the theorem. This is proved in our algebra class for the degree students. So this is about the P series. Then coming to the Basel problem, a very epoch-making problem. This is the problem which opened up the windows of the mathematical world to have a glimpse of Euler. Euler became overnight very popular in the mathematical circles of Europe because of the fact that he found out the sum of this P series when P is equal to 2. So it is nothing but infinite series of the reciprocals of the squares of the natural numbers. That is sigma 1 by n square. 1 plus 1 by 2 square plus 1 by 3 square plus 1 by 4 square, etc. A little while ago, we have established or we talked about the convergence of the series because P is greater than 1 here. Now this series confronted his guru, Johann Bernoulli. It confronted his guru's brother, Jacob Bernoulli also. So they could not establish the character of the series. Though it is very simple and innocent looking, it challenged the two great mathematicians in Europe of 17th and 18th centuries. The city in which the whole drama happened is Basel. That is the place where Euler was born. Euler's father was a pastor, and Paul Euler. And Paul Euler had known Johann Bernoulli. Perhaps they might have been classmates. So taking advantage of that fact, Paul Euler, though wanted Leonhard Euler to succeed him in the service of the church, he noted the interest of Euler in mathematics. Therefore, he took him, that is his child, to Johann Bernoulli and introduced this boy and his interest in mathematics, and requested Johann to give him some coaching in mathematics. John Bernoulli was an aristocratic person. He had no need for money. So he was against giving coaching or private tuitions. But this boy happened to be the child of his class fellow. He agreed to teach him some mathematics and allowed Euler to meet him for an hour or two on Saturdays, that is weekend days. So that is how Euler descended as a student of Johann Bernoulli. Johann Bernoulli was professor in the Basel University in Switzerland. There was no need for him to earn a few chips by way of tuitions, because he, as I told you, he is from aristocratic background. So this sigma 1 by n square was shown to Euler just for fun, and John Bernoulli asked Euler to find out its sum. That the series is convergent is known already, but to what limit the sum tends is the big problem. Now, how a mathematician gets a problem which forms the stepping stone for his great success in life is displayed in this simple story of Euler and John Bernoulli. A little while earlier, a similar story is recorded in the history of mathematics. Leibniz, who was a multifaceted personality, took interest in mathematics. And he found that his background in mathematics was not enough for him to do great things in the subject. Therefore, he thought there is a need for him to have some training, specialized training from a great mathematician. So he thought over the matter. It was 17th century area times. And then in those days, the French people were very famous mathematicians and physicists, great scientists. Even later centuries also, we find good number of mathematicians and scientists. Christian Huygens, a great physicist and a man famous for the pendulum, which is known in his name. So Leibniz went to Huygens, Christian Huygens, and requested him to give him some coaching in mathematics. The first thing that Huygens did was, in order to test the aptitude of Leibniz, he gave him an infinite series and then asked him to examine its behavior. And Euler took 2 days' time and presented to him the result of his findings that it is a summable convergent series. Let me not go into details of that because it is a diversion. So why I quote this problem is an infinite series has enthused Euler here. Earlier, in infinite series enthused Leibniz 1 century before. So Euler in the year 1734 showed that the series sigma 1 by n square converges to pi square by 6, following an ingenious method but not rigorous. Why he is not rigorous? Because he has taken the infinite series for sin x, that is sin x is equal to x minus x cubed by factorial 3 plus x power 5 by factorial 5 minus x power 7 by factorial 7, etc. This is an infinite series. And even a school-going child will tell that this is not an equation with finite power. That is ax square plus bx plus c plus d is equal to 0, ax square plus bx plus c is equal to 0 quadratic, ax cube, etc. cubic, ax power 4, etc. is quartic, similarly pentic equation, etc. So there is no equation which we can conceive as one with a degree infinite. But Euler treated the infinite series for sin x as a polynomial equation of degree infinite, and then considered the roots of that equation. You get infinite roots. From that he derived the sum of the series pi square by 6. So this is highly an objectionable methodology. Perhaps like this he did on several occasions things which are not rigorous. Maybe mathematicians thought that people like Gauss and Newton did not do such things. Therefore, those three, Archimedes, Newton and Gauss, are counted as all-time great. Newton or Euler could not be included for this reason perhaps. Now, as I told you, after examining the voluminous work, the trend-setting researches, the enormous contribution of Euler to mathematics, in spite of so many obstacles, he was almost blind for 16 years in the last period of his life. But yet, the quality of mathematics he produced is marvelous. So taking into account these positive facts, people now realize that small faults or his non-rigorous methods can be just overlooked, and he should be elevated as one amongst the all-time great. So later period mathematicians confirmed this result by rigorous methods. So that is the genius of Euler. Euler, who established that pi square by 6 is the sum of that infinite series, the Basel problem. Later on, mathematicians using rigorous methods proved that it is indeed correct. Then, if the power is raised to 3, you get a problem. And this challenged the mighty minds of mathematics for a long time. Euler could prove for p equal to 2, for p equal to 4, p equal to 6, up to p is equal to 26. All the powers sigma 1 by n power p, when p is even number. First even number is 2, then 4, 6, etc. He derived the sums of all such series, an astounding feat. for the days of Euler, when the calculus was just in the beginning stage and other advanced techniques were just coming up. So in those dark days, Euler could hit at these good number of series is indeed marvelous. Now, coming back to the case when p is equal to 3, Aperi attempted this, and in the year 1978 or so, he proved that the series is convergent, everybody knows. To what limit it converges is the challenging problem. So the limit to which this Aperi series converges is known as the Aperi constant, and that was proved as 1.2020, etc. And it was claimed, or it is proved, that this number is an irrational number. Now, as I told you, Euler has summed or gave the sum of the extraordinary series, which I have referred to earlier, sigma 1 by n power p when p is equal to 2, which is the famous Bessel problem, which brought Euler to the limelight. When p is equal to 3, it is Aperi's problem, I told you. Euler found the sum of these infinite series when p is equal to 4, 6, 8 up to 26, an extraordinary feat in those days of 18th century. And 18th century is declared in the literature of mathematics as the Euler century, because he was born in the year 1907 and died in the year 1707 is the year of birth. 1783 is the year of death. So except for the first 6 years and the last 16 years or so, the entire segment of time of the 18th century was his century. That is the Euler century. Then another interesting nature of this harmonic series is the depleted harmonic series. This is the harmonic series with all the terms in which a particular digit, say for example 9, appearing anywhere in the denominators are removed. Suppose you write the harmonic series. Wherever you find 9, you delete it. So the first casualty is the term 1 by 9. The next casualty is the term 1 by 19. The next casualty is 1 by 29, 1 by 39, and then 1 by 89. Then all the terms from 1 by 90, 191, 92, 93, 99 are deleted. So this is why we call it depleted harmonic series. So a particular digit, say for example 9, which I have described earlier, all these terms containing 9, if they are removed, the remaining is called the depleted harmonic series. It is also known as the harmonic series on diet, another funny name given to that in the literature. So this has been proved to be convergent. So that is the interesting point. So the depleted harmonic series is convergent. Then we will come to Dirichlet series. This is sigma 1 by n power x when x is a real number. It need not be an integer. When x is equal to 1, the Dirichlet series is the well-known harmonic series. And when x is greater than 1, the series diverges. When x is less than 1, it is convergent. All these things we know, we have seen. Then comes the Riemann zeta function. The Riemann zeta function, also known as the Euler-Riemann zeta function, is a function of S, a complex variable, which is analytically continuous. So from real variable, we jump into complex arena of complex variable and then define this function zeta S. So the origins of this Riemann zeta function is the harmonic series. So from the harmonic series, we get the Riemannian zeta function, a function of a complex variable S. And the basis for this is harmonic function and also the work of Euler. Now, the present times, lot of attention is being devoted to this Riemann zeta function, because Riemann hypothesis has been bothering mathematicians for a long time, for more than 150 years. In the year 1900, when Hilbert delivered his very famous lecture in Paris in the International Congress of Mathematicians, he listed 23 problems which Minkowski described as the homework for the mathematicians of the world for a century. It was homework for mathematicians of the world. For what period? Not for a day, not for 1 week. It is for 100 years. So that is the reputation that these 23 problems carry with it, uttered by the famous Hilbert in his famous lecture of the year 1900 before the ICM Congress, International Congress of Mathematicians. And what he said was, he included this as 8th problem in his list, and his desire, life's desire, was to know when it would be solved. See, a story is currently popular in mathematical circles. If Hilbert comes to life again briefly, the first question that he would ask is, has anybody solved Riemann zeta function or Riemann hypothesis? What is Riemann hypothesis? I will come a little bit. So that is the notoriety in one way, or the fame in another way, that is associated with the Riemann zeta function and the Riemann hypothesis. So Riemann zeta function continued. It plays a pivotal role in analytical number theory and has applications in several branches of mathematics. Riemann in the year 1859 gave a talk in the Berlin Academy. You know, Riemann was a shy person. He was not at all aggressive in his dealings with friends, or he doesn't speak about himself also. He is such a nice, calm-going, introvert person. He used to happen to be a student of Gauss, a famous student of Gauss. In 1859, earlier, he received an invitation or an honor from the Berlin Academy that the Berlin Academy was pleased to take him as a corresponding fellow of the Academy, an honor which is to be celebrated, a great honor for a mathematician. Riemann accepted this honor and went to Berlin to receive the fellowship. So, it is usual practice for the person who is inducted as a fellow delivers a talk. So he took advantage of that and gave a talk in the year 1859. The theme of the talk was the number of prime numbers less than a given quantity. You know, prime numbers are infinite and they cannot be counted. There is no formula to hit at the prime numbers. So eminent mathematicians tried their luck and expressed their inability to put forth a formula to generate prime numbers. So next best thing that they started to accept or popularize was to know how many prime numbers would be there less than a given number, up to a given number. So how many prime numbers are there below 100? There are 25 prime numbers. How many prime numbers before 1000, 163 or so? How many prime numbers before 10,000? So like that, people were interested in estimating the number of prime numbers less than a given number. So this culture was promoted and developed by Gauss, and Gauss has given wonderful conjectures and estimates regarding the connection of logarithmic function with the number of primes. So the famous prime number theorem, which was established, which was conjectured by Gauss and proved by later mathematicians. So now Riemann has chosen this beautiful theme for his lecture, the number of primes less than a given magnitude. Then in finding out this one, he said that he took the Euler's theorem on prime numbers and then went to the zeta function. Zeta in those days of Euler was defined for an argument which is a real argument, zeta s. Now he extends this zeta function to complex plane and then builds up a beautiful function, the Riemannian zeta function. Euler's basis, that is, he exploited the base given by Euler for zeta function. The values of zeta s for even positive integral values of s were computed by Euler. We have seen when s is equal to 2, 4, 6, 8, 10 up to 26, Euler has computed. Then another interesting feature in Euler is he established the connection between zeta function and prime numbers. That is a great giant step forward in helping Riemann in proposing his hypothesis and leaving the work of mathematicians to struggle to resolve this hypothesis. It is still a hypothesis unresolved. Then he established a functional equation, that's the Riemann functional equation, and this functional equation gives us some zeros. So zeros of the Riemannian function is the role, the pivotal role played by the zeta function in its attempts to resolve the Riemann hypothesis. If once the Riemann hypothesis is resolved, then we will know the mystery behind the distribution of prime numbers. That is the hope of mathematicians. Recently, great mathematician Ita, who passed away just 4 months ago, he announced to the world that he has a solution for Riemann hypothesis. He announced a date for its meeting in Heidelberg University, Germany. Hall or so. So he gave some outlines of his proof for Riemann hypothesis, and people did not accept the validity of the proof. You know, Ita, the great mathematician, he won the Fields Medal, he won the Abel Prize, and a very eminent mathematician of United Kingdom. But during the last phase of his life, he announced a result which he could not establish. Therefore, the Riemann hypothesis is still challenging the mighty minds of mathematicians. So the Riemann hypothesis reads like this: the non-trivial zeros of, as I told you, from the functional equation Riemann has produced, one evidently see that numbers like -2, -3, that even negative numbers are all zeros of the Riemann zeta. But they are trivial zeros. We don't get anything from them regarding the behavior and the mystery of prime numbers. So the mystery of prime numbers would be revealed only by the non-trivial zeros of the Riemann zeta function. And Riemann announced that these non-trivial zeros of the zeta function will have their real parts half. That is, you have a strip. In that strip, half plus I sigma varies. So these are the zeros of the Riemann zeta function. This is still an unsolved conjecture left by Riemann, and mathematicians are struggling. For a long time, the Fermat's last theorem bothered mathematicians for 3.5 centuries. Luckily, Andrew Wiles of the University of Princeton, who is now in Oxford University, has resolved this great historic problem of Fermat. Now, after the resolution of Fermat's last theorem, the theorem that is engaging the attention, the result that is bothering mathematicians is the Riemann hypothesis. So Riemann himself is reported to have said that he made attempts to advance a proof for his hypothesis, to establish his hypothesis, but his attempts did not yield results. At those times, he had priority for other items. Therefore, he says that it appears dispensable. That means to leave the search for a proof of the hypothesis appeared to be dispensable because his next objective of the investigations were awaiting his attention. Therefore, he left aside. Therefore, the hypothesis remains still a hypothesis. So, you see how a degree classroom lesson like harmonic series leads us to a peak in the field of mathematics and presents before us the great challenge of the Riemann hypothesis. So that is why I chose to present before you this elementary thing, though, the harmonic series, and how it leads mathematics further and further to higher levels of research. So with this, I conclude my presentation.